Welcome to another episode of the Mapscaping podcast. My name is Daniel, and this is a podcast for the geospatial community. Today, I'm talking with the co-founder and CEO of Duality AI, a company building virtual worlds or world models. We get into how Duality builds these environments from the ground up using everything from satellite imagery to photogrammetry. We also talk about training sensors like synthetic aperture radar and why real-world data just isn't enough sometimes. And there'll be a little story later on in the episode about robots trashing Airbnbs. And towards the end of the conversation, we get into the bigger questions everyone's asking right now. Is AI going to replace us or make us better at what we do? I really hope you enjoy this episode. Apurva, welcome to the podcast. And before we get started, how did I do with the pronunciation?
Pretty good. Yeah, that works. Yeah.
Yes. Okay. For the listeners, there's been a bit of back and forth at the start, like me being incredibly embarrassed about my lack of ability to pronounce any sort of slightly different name. So yeah, I appreciate that. Right. You are the co-founder and CEO of something called Duality AI.
Mm-hmm. That's right.
What is it? What does it do?
So Duality is a company that helps build virtual worlds or world models, if you will, for physical AI and robotic systems so that, these teams can move more quickly, generate synthetic data, validate their systems, inside world models. And that's really the journey we're on. So that's kind of where we sit.
World models. We're definitely going to come back to that a little later on in the podcast. How did you get into it? What's your background? Where do you come from?
It's a very different world that I originally started in. Actually, after doing computer science, I studied computer science and spent most of my career actually in animation. I had my first animation class at Texas A&M, fell in love with it. So I spent my first part of the career at a small studio in California called Pacific Data Images that later actually turned into DreamWorks. And then, bulk of my career at Pixar, where I was there for over a decade, part of the technical brain trust there. And that's really where my love for virtual worlds and really working on creating a sort of synthetic version of reality. It kind of goes back to that time in my career. After that, I met my co-founder, Michael Taylor, or Mike. And Mike is a roboticist. So if I'm the sort of pixels, he's the atoms in this equation. So he's been in love with robotics his whole life. Controls engineer, was led field robotics at Caterpillar for most of his career. And quickly realized, deploying these house-sized machines at mines in Australia, that even in a controlled setting like that, it's very difficult to avoid edge cases and strange things from happening, like people driving on the mine where they're not supposed to, for example. And, he concluded as a, very responsible roboticist that, hey, the only way to really manage that situation is you're never going to get all the data you need and all of the validation you need in the real world. And so you really need to have virtual worlds or world models to actually train systems safely. It's just like when you try to learn to be a pilot, you don't go sit in a real plane right away. You kind of fly a simulator first and you get your bearings. And it's the same idea with cyber physical systems, whether they're robots or physical AI, whatever. You don't want to unleash them on the world till, they've learned the basics, they're safe, they kind of understand how to navigate different situations. We met through a common friend and, we just started talking about like the importance of simulation in that context. And it was a, point in both of our lives and careers where we're like, hey, maybe we should start a company and kind of see where this goes. So that's sort of how we started Duality. This was right around COVID time. So probably in hindsight, not the best time to start a company, but maybe, that's fine too, right? Because we were all just sitting at home anyway. So
yeah, and when is the best time to start a company? This is the other question, right? Because I remember thinking with my wife, when is the best time to have a child?
No.
I don't have a great answer to that.
All times and no times, I suppose, right?
Exactly. Hey, I was just thinking about training machines, and this is a bit of a tangent here, robots. And so currently there's a lawsuit happening in San Francisco, where a company training their robots, they were renting out Airbnbs, going there, setting up everything, training their robots, destroying the place, and then leaving again. And I guess you're solving that problem for them, right? You're saying, hey, let's do this in a virtual world.
Yeah, no, I saw that actually. And there's another company that is going around basically offering to clean your house for free. With humans, not with the robots. They want humans to come in with instrumentation to basically clean your house for free so that they can collect learning data. And it's an interesting way. Of course, I think real data, and we can talk more about this obviously as we continue, but we never say that real data is not valuable. Real data is still the highest fidelity data. It's going to teach you things that, even the best sort of highest fidelity model is not necessarily going to catch, right? Especially the things you don't know, right? Like what Rumsfeld used to say, right? Like, I mean, you got to go find those things. And so real data definitely has a really important purpose. It's just not adequate. It just does not provide you with critical mass. So no matter how many free houses you go clean and how many Airbnbs you trash, you're just still not going to get enough variety. And also, like, if you look at it just statistically, you're going to have gaps. You're going to have biases in your data sets. You're going to have a lot of, like, San Francisco houses, but not houses in Florida or somewhere else, right? So you're always going to land up with sort of both, high density areas and very sparse areas in your data set. And part of, again, what synthetic data can do is very intentionally fill those gaps, basically.
Don't get me wrong. We're definitely going to get into that in just a second. I'm just trying to sort of set the scene a little bit for people. Hey, we talk about creating these 3D worlds, these virtual realities. I'm not sure if it's still a buzzword, but at least in the geospatial world, we're often talking about digital twins. For you, are these the same things, or are there slight differences between them?
So I think digital twins, at least in the way we think about it at Duality, and I think at least some people think about it, is as more as building blocks, so compositional elements, right? So if I take several digital twins and put them together, I should get a virtual world or a scenario of some kind of, and that's, at the end of the day, you're not collecting the data from the digital twins directly. You're collecting the data from the composition of those twins and the interplay between those twins. Now, this gets a bit fuzzy because there's a question of what's the granularity at which you think about a twin. And so you could say, hey, a whole city environment is one digital twin, right? And certainly there's nothing that invalidates that kind of an assumption. But what we love to do is have a lot of both, modularity and reuse and interoperability, right? So by keeping digital twins at that sort of level more of objects or systems that you can compose quickly into more complex scenarios, is part of how we bring that reusability and that interoperability. But yeah, I mean, there's similar things. Now, there is a difference between 3D assets and digital twins for sure, right? So 3D assets, the world I come from, right, they have much more to do with appearance. So even if you have this beautiful Pixar animated character, a rat or a fish underwater, the life in that character is coming from an animator, a human who's actually animating that model. And the model has articulation. So it has a certain kind of skeleton and deformation to it. So when you start bringing in those other levels, beyond appearance, those levels of behavior and how this thing reacts to physics, how this thing actually moves, I mean, it can go all the way from simple rigid body physics to like a full autonomy stack inside an off-road vehicle, right? At the end of the day, that's the behavior of that system. And again, that is modular to the digital twin as well, right? I can take that off-road autonomy vehicle from an arid desert environment and I could put it on the surface of Mars and it can still drive, right? So in that instance, the digital twin would be the vehicle and the environment, and I could compose that into different kind of configurations, each one giving me sort of unique information. Even though the twins are the same, because of the way I've composed them in different configurations, I can get unique information from that.
So how should we best talk about what you do going forwards in this conversation? Should we call them 3D worlds, virtual worlds?
Let's call them digital twins. I think that's fine.
Okay,
Yeah.
Okay, cool. So how do you create yours? My guess is you're not going out and scanning real world environments, or maybe you are. How do you create them?
I mean, it's a combination. Actually, I mean, we use a variety of techniques, everything from very talented asset artists on the team who can take even a photograph and create a very good representation of that in 3D, to scanning. We've done photogrammetry type of things where we are actually going out and scanning these things. And then one of the things for environments in particular, that is very interesting is we have a geospatial pipeline which can start essentially from DEM data and satellite imagery. And then knowing about the biome in a particular part of the world, we have a catalog of different vegetation and bushes and grass and trees, etc., that we can again compose very quickly into simulation ready environments. So, right, again, at ground level. So these are environments built kind of ground up. And one of the benefits of doing that is everything is annotated. We know a blade of grass is a blade of grass, and we know that a tree is a tree, which is really important for learning. Again, when you're putting AI systems within these environments to learn, they really need to know what's what. And so that's part of the advantage of building twins in this way.
When I think about, you used the example before of these earth movers moving around in a large Australian mine.
I think it was dump trucks in that case, but yeah.
The dump trucks, like I can imagine there's the physics of it. How can I power myself up this hill with the gravel? Can I fit on this road as the dump trucks?
Yeah.
I'm wondering, so there's that side of it for me. And then there's the other side of it, like training the sensors. If these things are going to move autonomously, that you're also kind of changing the sensors in that visual environment, in the virtual world that you've created. So my question is, the physics, the size and the shape of these objects that you're putting into these digital twins, the reflectance levels, different stones reflecting according to their mineral makeup, for example. Mm-hmm. Is that something that you're building into these assets? Like, is that part of it?
So I'm gonna take a kind of a step back and answer first, just frame the answer, right, a little bit. So what we found, and as having done this now for several years, is that for this kind of synthetic data to be useful in training AI systems, you kind of really need two things. And I'm going to talk about the first thing first, which is the data needs to be accurate. It needs to actually be indistinguishable or predictive of what will actually happen in the real world, right? So if the data looks good to the human eye, but it's just made up and it's not grounded in physics, then it doesn't make any sense, right? We could make movies that way, but we can't train these cyber physical systems that way. You kind of need data that's indistinguishable and accurate. And so what we do, and going back to, you asked the question earlier about like, well, where do we look at the real world for inspiration? Yeah, sometimes we'll go scan the real world. But in other cases, for sensors, for example, we will actually calibrate the virtual sensor to real sensor. Even if we have a small amount of sample data, we can say, okay, let's create an virtual environment that is similar, and then let's make sure we are calibrating our sensor. Because sometimes it's not even about the physics of it, but the sensor itself may have specific noise characteristics and other features in it that become kind of part of the data. They become a part of what comes out of the sensor. So you really need to calibrate the sensor as well to make sure that the virtual sensor will actually match the real sensor in that indistinguishable way. The same with systems. So if it's a vehicle, we will try to get the specifications of that vehicle and see if there's enough information there. But we might do additional data collection. Like, when you accelerate, how quickly does the vehicle pick up speed on a road of a particular type of friction or a turning radius? So we do look at the physical system and we collect as much data as we can about that physical system and basically bake it into the digital twin, right? So that it will behave in that sort of predictable way. Now, exactly which parts of a digital twin or a model do you get right? Because at some level, all models are abstractions. There's a simplification there. So that really depends on both the domain in which you're operating and the level of fidelity of the data that is required to actually successfully make those systems work within that domain. I sometimes joke about this with clients because, clients always want more, right? That's part of how it works. And at some point you're like, well, if you really want it to be completely like reality, you should go work in the real world, right? Because you're not getting any benefit of using modeling. All modeling has simplification in it. And so then the question becomes, what's the adequate amount of fidelity and modeling accuracy that, again, I would argue is always domain dependent. And again, it's a simple example, right? One of the first movies I worked on was ants. So if I'm working on ants, right, a blade of grass or even a drop of water on that blade of grass has very specific, like, soft body physics on it. I need that, right? Because at the level of the ant, that is so important. But if I'm working at the level of human scale, right, that, okay, I want to show drops of water on things if it has just rained, but I don't need them to have that kind of tension, surface tension to them to actually make the world work. So scale and fidelity is always domain dependent. And so I think it's important to keep that in mind. And then making sure that you're modeling the right things for solving the problem that, at the end of the day, a customer has.
So let's say I came to you and I said, look, I've got this new SAR sensor and I want to throw it up into space and fly around the world and collect data using that. But before I do that, I want to know if it's going to work. Would you be able to help me with that?
Yeah, we actually have some space-based customers. I mean, that's a really interesting domain because data isn't readily available, or whatever data there is, it tends to be very, very limited. Now, I think here we kind of need to introduce a slightly different concept as well. So when we talk about world models, we sort of generally divide them into explicit models and implicit models, or classic models and more generative models. What Duality does is we take advantage of both types of models. We look at the problem and we say, hey, what's needed? What is needed here to solve the problem? But one of our core products, Falcon, is a digital twin simulator. So that's kind of an explicit world model, if you will, right? And one of the nice advantages of that is you don't need a priori data or certainly a lot of a priori data to make sure that that model is correct. Like laws of physics apply anywhere in the universe till someone like Einstein comes along and says, no,
Yeah.
it's wrong, right? But for the most part, I mean, there's a lot of validation behind these laws, and that you can rely on them. Laws of thermodynamics or rigid body dynamics, whatever it is, right? That they will work here, they'll work on Mars, they'll work anywhere else, right? And so because of that, you can have models that don't have a very prescribed kind of learning domain. Now, generative models, on the other hand, they're always trained on data. So in some sense, they do an amazing, like a phenomenal job at a very high fidelity of interpolating learned data, but they have a much harder time going outside their learning domain. So when you have unique situations, unique configurations, it becomes a little bit difficult for those systems or that kind of modeling to work, right? And so that's why you kind of want to use a combination. So in something like a space, having a space system using sort of those explicit solvers and explicit models lends itself really well. But, there is data. So one of the data is, like we were talking about geospatial environments before, there is good data around star fields. Now, if I want to do localization out in space, I don't have roads and buildings and sidewalks or whatever to pick up on, and do localization, but I can use the star field. So if I can create a 3D star field that is a good representation, then that can become very important data for that domain. And certainly think about the fidelity there. I'm not modeling a star. It's very, very far away, but I'm modeling it as almost a point in space of a certain intensity, which then allows my model to start learning from that.
That's a really interesting example. And it made me wonder, does that mean that you would sort of break the problem down into all these sort of sub-problems? Like, okay, well, how do we keep our satellite pointing at Earth? Well, we could use star fields. Let's model the star field and then fly the satellite around there and see if we can keep it pointing in this one direction based on that. And then another problem might be, do we know that the atmospheric correction is working? Am I understanding this correctly, that you might model these things separately?
So I think that in some cases, we'll model them separately. Sometimes we'll model them in combination. But at the end of the day, we are often looking also at the output of the sensor, right? So that whether it's a synthetic aperture radar sensor on the satellite or a very high resolution camera, you're going to look at the output of those sensors as well and say, hey, what all is potentially going on here? What's the combination of effects that are happening here? Yeah, from a modeling perspective, how do we break them down into manageable pieces. And then again, keeping that reuse in mind, right? So if I'm building a star field for, let's say, satellite docking, could I then use that same star field in a different kind of use case as well?
Are you going to end up with a bunch of these sort of digital twins, virtual worlds that on the shelf that I can
We
come and
do, in
choose
fact,
from?
have a catalog, which is, I think we're up to like several thousand now, right?
Wow.
And our customers get these, right? So if they become Falcon users, they immediately get to start bringing these different digital twins into their scenarios, right? Whether it's environments down on Earth, underwater environments, space environments. So yeah, that's the whole idea. Like, let's model these things again for that kind of data collection, for that kind of accuracy. And then what we find is that the most interesting data comes out of putting these different digital twins together in different combinations and different configurations.
Yeah, that makes a lot of sense. Are you slowly but surely improving these environments with each run? My guess is like different sensors, different parameters. I wonder is there a feedback loop that feeds back into each individual environment?
Yeah. So, there are patterns and there are certain areas where we are much further along. For example, in terms of off-road environments, we have done a lot more work. And so, our understanding for the team becomes more sophisticated. The kind of digital twins that we've already got in the catalog become more sophisticated. We've done less work, for example, in on-road autonomy, right? So city environments. We absolutely do have built environments as well. But, again, they do tend to be sort of a bit more domain targeted, right? So if you're trying to look at, I think there's another project where we looked at sort of city environments where you're trying to do civil planning around exit routes and things of that nature, high density crowd areas, and how do you manage those situations. But that's a very different kind of consideration, right? Than a car that needs to drive on the road and is concerned about, like, hey, is the sidewalk broken? Is there a yellow line on the sidewalk or not? So those considerations start to change and then drive where you're focusing a little bit more.
In terms of, I want to say real world data sets, and what I'm thinking about here is you mentioned digital elevation models before. We have them in various resolutions across the planet now. We have access to satellite data for the entire planet, fundamental data sets, at least in my mind. I guess it depends on what you're doing, but we have them and we have an archive of them. What other data sets are you pulling on from, to create these worlds, like to make them as realistic as possible?
Yeah, no, so there's some really good public data sets. Like NASA has some really nice elevation maps from the European Space Agency. Actually, there's some really nice satellite maps as well. Umbra is a great data set for synthetic aperture, SAR data. So there's some really nice public data sets out there. There's obviously in the commercial side, there's also higher resolution data sets as well. And in those situations, often we work with specific customers, right, who are playing within that supply chain, whether they're OEMs or they're processors of data. And obviously in those situations, the sensors we have are canonical sensors, right? So they're kind of ground truth sensors in a way. So they, like our synthetic aperture radar sensor works with ray tracing. So it kind of recognizes that there's a geometry and then does some, complicated sampling on that to come up with an output for the SAR. So in those situations, a lot of the work, so that calibration work I was mentioning before, we look at the customer's data, whether it's their own sensor or the sensor that they're using in their commercial system. And then we tune our canonical sensor to basically match that. So there, of course, I have to tell you, like, there's not a lot of that stuff that we can share publicly, but there's some incredible, like, the resolution just blows you away. It's incredible resolution.
Okay, can't share what you're using. I get that. What are you missing? Like, if I could go out and create a data set for you that you would be like, if we had that one, what would it be?
So something that comes up from time to time is context has a shelf life, right? And sometimes, getting, especially from, these kind of satellite data sets, relevancy matters, like, recency matters, relevancy matters. So that's the part where now some of it we can help fill the gap. So for example, weather changes and things of that nature, we can introduce also into the data set. But fundamental shifts that, you need to pick up in the terrain or things of that nature, like obviously having a data set that captures that or captures that in the relevant context would be super helpful. That's one example, right? Like I think recency, relevancy, I think makes a difference.
And this is in environments that change a lot, maybe urban environments, for example, where it's...
Right, that's right. So environments that change a lot. Like we can intentionally bring, like in a marine environment, like we can bring in ships, we can bring in other things that, let's say, you're trying to detect. So that is very much something we can bring in as digital twins. But the sandbox environment itself needs to be relevant as well. And sometimes it can be a little tricky to get good high fidelity data for that.
We were talking about SAR data before and modeling how a sensor would react, the results of a sensor in a specific environment. And I was wondering about the texture of things, because I guess concrete steel reflects differently than dirt. How do you deal with that? Is that something you create, or you're trying to, and I guess texture changes throughout time, like how much has it rained the last little while? Is there snow on the ground? That kind of thing.
Yeah, now we're getting into how the sausage is made.
Yeah.
Right. Same thing for infrared sensors as well, right? Like, I mean, the characteristics are different than visual characteristics. And the approach we take to that is, and I'll explain the approach and I'll explain the rationale as well a little bit, is that, we have our own internal proprietary technology, which will look at the sort of visual spectrum response of a material. And from that, try to predict, is it a dielectric? Is it a conductor? How is it likely to behave through the rest of the spectrum? So it turns out that actually a lot of materials are reasonably well behaved. And you can kind of get a glimpse of that material type by looking at its visual response. And then you can predict from that, how it will play out through the rest of the spectrum. Now, that by no means is true everywhere. And definitely there are materials that can have multiple peaks and troughs and so on, right? And there are more complex materials that also have layering, right? So dust over metal can have a fundamental shift in how that material will then respond, right?
Yeah.
So we have this sort of default material for infrared, so short, medium, long wave, or for synthetic aperture radar responses that you'll get kind of out of the box. But then, you want to make sure that it's responding very much like the real material. Then we also have ability to author those materials further and control the response across the spectrum, right?
Okay. Yeah. So it sounds like, to me, my naive brain, it sounds like you can predict a lot just from looking at it. So the visual response, like RGB, the way it looks can help predict the way it's going to react in when you shine other kinds of radiation, or I guess,
exactly.
Or yeah.
You're basically guessing what's the material characteristic.
Yeah.
Right.
And if I want something else, I say, well, it's really important for me to know what it's going to be like with dust on this environment. Then you can just create that for me, that specific
exactly, or an engine, right? So an engine looks a certain way, but if the engine is hot, its response is very, very different, right? And in fact, its response will change over time. So we allow that level of sort of finer control. And the rationale behind this, again, is that, when you are trying to train AI models, right, typically you're looking for objects of interest. And then the rest of the image or the rest of the visual field is really clutter. And part of what you're trying to do is get your model to really learn the signature that matters versus everything else. And so, it doesn't make sense for our customers to invest a ton of time on making sure clutter looks perfect. I think what's more important is that the signature you're really trying to detect looks spot on. And then everything else needs to be there to confuse the model and for the model to become resilient, more resilient, more robust. So that's kind of why we took this approach. So building, yes, we could create an environment where everything has IR signatures on it, right? But that's not a great use of anyone's time or energy.
Yeah. I was just, when you said like everything is there to confuse the model, I was thinking, it's only clutter when you've identified the thing that you're looking for. Until that, it's like a potential
it is
thing,
a potential thing of interest. That's right.
Yeah.
That's right.
Hey, in a previous conversation, we talked about some work you did in Melbourne with flooding. And I think this is a bit of we've been talking about machines and sensors.
Yes.
Could you walk me through that example, please?
Yeah, sure. So this was work we had done in partnership with Amazon Web Services, AWS, awesome partner. We actually in the AWS marketplace as well, for Falcon. But in this case, they were building internally a very highly parallelized distributed simulator with like that can simulate millions of entities essentially. And so they had picked this interesting use case of like when you have an emergency within a city, and let's say you need to route emergency response, for example, in a cardiac event, even like if you can get to the person within the first 5 minutes, I think there is a significant chance of survival, and then it drops off very, very quickly from there, right? In case of a serious cardiac event. So that was an interesting problem because it was a real problem, a problem where there's a very real outcome if it can be solved better with data. So what we did there was build a city and then come up with like, okay, in simulation, I want to have a decision support system that can actually tell me how to best route an ambulance system to a particular part of the city, given congestion and given sort of bottlenecks within the route. And we also connected that. So there was a little bit of intelligence as well there. So the traffic system can obviously be coordinated with the ambulance. So you might make different decisions because you're not just looking at traffic and like when you're looking at Google Maps or something, it's just like, hey, this is the state of the world. There's nothing you can do about it, right? But for an ambulance, you can control the lights and control its access to roads. But then you still have congestion. Some places you will have an intersection that is blocked. Now, what do your traffic lights, even if your traffic light is green in your direction, if the intersection is blocked, the intersection is blocked. So we also then had a handful of human agents that essentially people could teleoperate. And those human agents could then clear out intersections. So you had this sort of fairly sophisticated system where you've got the ambulance driver, you've got the dispatcher who's able to look at the whole context. The ambulance was autonomous, so it was driving itself. And then you had these traffic police, right? That there were 3-4 of them that you could place at key points within the city. And then all of these systems had to coordinate across multiple. So these are different kind of clients, each responsible for a different part of this very large simulation space. And then, you needed to coordinate all of those agents together. So that was kind of the focus of the project. There's a really interesting use case, but also then there was some technology that we were trying to push forward with AWS in that situation.
It sounds incredibly complicated. So I get the idea of a mine, like this open cast mine that we're talking about, or like a desert situation, but a city with all of those moving parts. That sounds ridiculous to try and model.
Here's the interesting thing. How complicated do digital games get these days? Incredibly complicated, right? And
yes.
It's like this classic example of dual use, right? Where people building games and people like me who've been making movies for a long time. I mean, this is why we started Duality, right? It's going back to the beginning. We've been working on these kind of problems. Like when I was at Pixar, right? If the world I'm building, the virtual world I'm building, right? The computer generated world has to go where the story wants to go. I can't be like, yeah, no, my mod sim solution doesn't do that. Right? I want a rat cooking, in a kitchen in Paris. It's like, great. Okay, let's figure out how we're going to do that. Right. So that's sort of the thinking here, right? It's like we really want these worlds to be very versatile. We want them to be usable in different kinds of situations. And so a lot of the underpinnings of Falcon, the platform we've built, is really to get at that. Like, how do you have the diversity, the flexibility that you need in building these kind of context, while at the same time having a high level of control as well. So that intentionality that you need in the kind of data you're trying to create for a particular type of AI system training or for a particular type of autonomy system validation. So you kind of need to have fidelity, you need to have diversity, you need to have control. You need all of these things. And it's not like, oh, give me 2 out of 3. So we learned very quickly on the entertainment side that the way you do that is there is not a single monolithic solution, right? You have a toolkit. You have different tools, you have different approaches, and then you kind of put them together to solve the specific problem. And so that's also the approach we take with Falcon, our platform. It's like there's a lot of different ways at getting to a solution, to solving a problem. and then you pick the right ones that work in a given situation. So that's why the same solution that we talked about doing sensors for SAR or that off-road vehicle is the same solution that you can actually use to simulate cities.
How much overlap would there be between, let's think about Melbourne now as a city. It was probably very, very different from, I don't know, Jakarta as a city.
Okay.
If I want to run the same simulation there, like what changes would you need to make?
So you'd have to build a new twin, right? So and people are, cities are getting pretty good about this too, right? They're starting to have digital representations because they want people to be able to pick up the city and do things inside it digitally. But that doesn't answer your question. So the geospatial pipeline we have is more versatile, I would say, in being statistically accurate rather than being literally the same. So we are very good at doing forests, distributions of biomes, right? That we do very well. If you have very specific man-made structures, of course, we can do that using, building out those things, pulling them from catalogs or from existing digital twins that are there. So Singapore, for example, has a really nice digital twin of the city, so we can pull that in. So we are definitely pulling those things where they exist. And where they don't, we can build them. But when it comes to those sort of more organic biomes, we are able to build them using more geospatial data as well.
This is always a really tricky question for founders to answer because we can do everything. But like, if I have a certain kind of problem, when should I not come to you?
Yeah. So we are building a physically oriented world. So that's the key, right? So if you want to build a digital twin of a virtual patient because you want to run clinical trials on that patient, for example, or you want to do drug discovery on a digital twin, we're not the right people for that. But if you're trying to create a physical version, like a virtual version of the physical world, whether it is for robotic systems or physical AI systems, whether that's across industrial applications, across defense applications, across logistics applications, like that's where we really excel.
Independent of scale. So no matter what scale, it's physical. If it's physical, you can do it.
I would say that generally at the human scale is where we excel. Like if you're starting to get down, like if the eye can see it, we can probably model it pretty well. But if you're starting to get down to the atomic scale or molecular scale, we're again not the right people for that.
Yeah. Okay. Is that because things behave differently when they get very, very small, or is it because the availability of data? Or
yeah, I think it's like we talked about that catalog before, and every tool again lends itself to working. It's like I could force Falcon to do molecular scale stuff, but there's probably better tools for that. And so why try to make the shoe fit in a way, right? There's a very large class of problems we are able to solve with what we have. And there are other solutions that are better for other parts of this ecosystem. I will say one thing, right? Which is that this general approach of digital twins, right? So thinking about digital twins as building blocks that you can put together in different configurations, right? And then having essentially a simulation engine that can then move that scenario forward over time and generate data of interest. That is pretty universal. I would say it applies even to that virtual patient digital twin we talked about and the drug discovery digital twin we talked about. You can still decompose the problem in the same way, irrespective of domain.
We're sort of winding down the conversation a little bit now. And I want to ask a few sort of broader questions. And at the moment, the way the world is now, AI is the thing. If you're not doing something in AI, you're not doing anything. And we're all wondering if it's going to take away our jobs and destroy the planet. And so the pushback, and we're pushing back on this idea of, we're saying slop. When is it slop and when is it good enough? Because there's a fine line there. I think you introduce too much complexity and it's needless complexity, not enough, and you could be accused of creating slop.
So again, in that conversational spirit, I'm going to take this in a slightly different direction, right? But I'm basically a humanist, right? I believe very much in the human, in the human experience, right? And I do believe that, AI is the new thing, right? And I mean, it's a new whole thing that's been around a long time. But in its new avatar, let's say, right? Obviously, it's a mistake to discount like how versatile and how amazing human intelligence has been and has, continues to be, right? So from that perspective, we believe that a lot of what AI is enabling right now is actually for human intelligence to be able to go that much further, right? For me, it's not a question of is AI good or bad or will take jobs away or not. I think the more interesting question is like, how do we actively work to get more people to be able to leverage AI to work better, work more efficiently? And one example of this is, we've been running these sort of hackathons, so geospatial, actually, geospatial in nature on Kaggle, which is a site where you can run different AI competitions and hackathons and things. And we've been doing this, and I think Nadine as well and Lumate, right? So we've done this in partnership with them, where we're actually making it possible for people who are trying to, who are learning to be AI engineers, to train AI models in the geospatial space, to be able to essentially create data on demand, right? Hey, let me put a building here. Let me put two buildings next to each other. Let me put a water body there. Let me see how that changes the ability of my model to recognize these features. So this idea that, hey, as an AI engineer, you're not limited by the data someone gave you, but that you can actually intentionally go create data yourself. Now that brings a whole different kind of intelligence to the model training process, right? So that, yeah, sure, nobody's going to sit and look through millions of images. We want AI to do that, right? Because it's more efficient and that's awesome. But the human who's behind the scenes making that AI model can now start to use their intelligence very effectively to actually curate data, to create the data themselves where there are gaps, right? So from my perspective, it's like whenever one of these big technology things happen, like it just elevates the field for everybody, right? And it's not like, oh, if I will use AI, then I will be better than everybody else and I can, fire my staff. You can, because now that's the table stakes. Everybody has that. So you're back to your team, right? And how are you going to basically get that team to be more efficient and more intelligent and, tinker with AI and figure out new ways to put it to use, right?
You did take that in a slightly different
I
angle,
did.
but I appreciate that. And that is fine. But let's carry on the same trajectory. What should we all be doing? Like, my guess is we should all be tinkering, we should all be playing, we should all be experimenting. But do you have a different take on that? Or what do you recommend people do now to sort of prepare for this world where we're going to all get the Iron Man suit, as it were, the bicycle for the brain?
Honestly, nobody has the answer to that, to be honest, right? Like we're all figuring it out as we go. For me, what has served me, like, over my several decades working in different, like really interesting, like, when I started in animation, we didn't know how to do fluid simulation. We didn't know anything, right? We didn't know how to do hair and fur and stuff like that. Starting with autonomy, right? Like some of the same, seminal problems around like, how do you make data that actually will work for training and so on, right? So I've always enjoyed kind of working on problems, on puzzles, right, that are unsolved. And so for me, what works is to always be naturally curious, right? And also be like humble, right? Like I think in a lot of these cases, there isn't necessarily a single sort of silver bullet, right? There are things that used to work well before and they still serve us. So think like explicit simulation. And then there are new things, that open up new doors. And then a lot of the interesting things that we can bring as humans is also that sort of lateral thinking, right? If I connect this to this, that actually leads me to this pretty novel place, right? So for me, that curiosity and that willingness to say that, hey, there are potentially many facets to any problem or solution. And a part of, I think, what is very unique about us as humans is the ability to be able to see that, to get out of our own head, as it were, and look at the world or look at problems from different perspectives.
Do you see this technology as being fundamentally different from other technologies that we've been exposed to throughout the years?
I think that from a social perspective, I think it is like other disruptive technologies. I think in the middle of it, we are in the middle of it, so it feels like, oh my God, nothing like this has ever happened before. But I think fundamentally, from a social standpoint, as humans, beyond technology, there are so many relationships, other aspects to what makes us human, right? So from that standpoint, I think everything is novel, but, at the same time, it's also potentially a movie we've seen before. I think technically it's slightly more interesting, right? So I think if we look at so this is now I'm kind of really jumping off the deep end here. But if you think about a lot of how science has developed and technology has developed, right? It's been about virtualization. Like we started with very physical things. And then over the decades, we've been moving, first down to the atomic level for semiconductors and things like things have been, miniaturized, and then they've disappeared altogether because they've been virtualized, right? In a sense. And certainly part of what we do at Duality is very much on that virtualization path, right? But also if you look at games, right? Like playing physical games, soccer on the field, not watching on TV, I mean actually playing versus playing it on your Nintendo or whatever, your PlayStation. I mean, it's a kind of virtualization, right? I think AI does fundamentally create an intelligence within virtualization that can rival our intelligence. I do think that from that perspective, it is a new vector, right? Like we are not used to an intelligence that potentially exceeds ours, right?
Yeah.
And not in all instances, right? Again, I don't want to be like the same thing I'm saying before, right? There are many facets to looking at a problem or a solution. So I don't think like it's true everywhere. But, if you ask me like, what would we want Duality to be known for, right? In 10 years from now or something like that, I would say that, if we can somehow, through the work we are doing, this sort of physical manifestation in the virtual space, and then making AI be able to think about that, in a safer, more predictable way, and also leveling the playing field. So one of the things that is very interesting about, virtual environments is that it's the one place where human intelligence and AI intelligence can collaborate and they can play with each other. They can learn from each other. So I think that would be the thing we would love to be known for, is being, part of that bridge that connects these things together.
Like after you've dominated the world with Duality,
no intentions of dominating the world.
You should consider a new career as a podcast host. I had that exact same question in my notes. I was like, when you said, virtualization is the vector that things are heading, I was like, that's great. That's a great segue into the next question. But then you said it, you asked yourself the question, and then you answered it. So consider being a podcast host once you've conquered the world. You've got a knack for it. This is probably a really good time to round up the conversation. Thank you very much. It's enlightening. And I particularly appreciate the piece at the end. That was probably the most challenging for you, right? Because you're having to sort of guess what's going to happen in the future and share your thoughts. But a lot of the other stuff was like, well, these are the facts. These are what we're doing. This is what we're seeing in reality. People are asking us to create these environments, to test these instruments. So also fascinating, but I think it requires a little bit more of a personal sort of step forward to come on a podcast and say, I think the world's going to look like this, or this is what I imagine. So I appreciate that.
I really appreciate that. Thank you so much, Daniel.
So thank you for your time. I will put some links in the show notes. Is there anywhere in particular you want to send people? Is there something they can go and test for themselves or play around with or see? Or
so we have, some really great resources and blogs that talk about some of the, go deeper into some of the things we discussed today, Daniel. So I would also encourage folks to check out, duality.ai/resources/blogs. I mean, you'll find stuff there that hopefully gets deeper into some of the areas we touched on.
Wonderful. Hey, thanks again for your time. Much appreciated.
Of course. Thank you so much, Dan. See you.